Everybody, let us talk about classical versus quantum communication. In classical communication, the Shannon entropy quantifies the information in a random variable, which is a very well established fact as per the communication theory. In quantum communication, we also want to quantify that how much classical information can be extracted from a quantum system. Before we get into the quantification of the classical information in quantum systems, let us prove one very important fundamental result in quantum mechanics, which is known as no cloning theorem. As I said, this is a fundamental result in quantum mechanics, and it says that you cannot make an exact copy of an unknown quantum state. If any unknown quantum state is there, you cannot make an exact copy of that. So, this is a true result in quantum mechanics, and this result is actually the basis of modern quantum cryptography. Let ket psi be given by alpha ket 0 plus beta ket 1, and we know that cloning means copying. So if the cloning is possible, what should happen? Let me explain that. If there is a qubit ket psi, and if we take another blank qubit ket 0, so after the cloning, if let us suppose that the cloning is successful. So before cloning, we take a qubit ket psi and we take an extra blank qubit ket 0. But after, if the cloning is successful, at the blank qubit position, ket psi should also be copied. So this is the result of cloning if it is successful. We know that it is not possible to do the cloning. And this, we will prove this by way of contradiction. We will assume first that the cloning is possible, then we will try to make a justification that cloning is not possible by a reasoning method. Now let us try to prove no cloning theorem. And we say that let there be a unitary operation such that for any input state ket psi, the cloning is possible. So we apply this unitary operation. As I said, the possible input state formation that we have considered, we considered a qubit ket psi and a blank qubit ket 0. There is a tensor operation between the two, and we apply this unitary operation. What should result into? The blank qubit should also be replaced with the ket psi because of this unitary operation. Let us say that some unitary operation exists. And if this unitary operation exists, it should work not only for ket psi, it should work for all the quantum states. Let us take another quantum state ket phi also. So we have two states now, ket psi and ket phi, and let us apply this unitary operation on these two quantum states as is just shown here. So unitary operation applied with ket psi and this blank qubit, we get the chron of both ket psis, and unitary operation applied on ket phi and chron operation of ket phi and ket 0, we get ket phi at both the places. Now let us take the inner product between left hand side and right hand side in these two equations. So once we take the left hand side inner product, ket psi will go with ket phi, ket 0 will go with ket 0. This is the inner product. And since ket 0, the inner product between 0 with itself is 1. So therefore only one term is left, which is the inner product between ket psi and ket phi. This is on the left hand side. On the right hand side, we have ket psi inner product between ket psi and ket phi, and ket psi and ket phi 2 times. So therefore we will get a square of the same term, which is the inner product of ket psi with ket phi. Now if we equate the left hand side and the right hand side, you see that you have a situation where one term is equal to the square of its term, right? So this is possible only in two cases: when the term is 0 or the term is same, both are same, that both are equal to 1 actually. If so, in the first case, if this is equal to 0, that means the inner product is equal to 0. In that case, the states are orthogonal. Or in the second case, this is equal to 1, and in that case both the states are the same. So cloning is possible only in two situations: if the states are orthogonal and if the states are same. So therefore we can we can say that the cloning is only possible when the states are orthogonal or identical. Therefore cloning is not possible in normal situation for any unknown state. This proves that by contradiction, of course. Now implications of no cloning. Because of no cloning theorem, we achieve quantum security, because it is impossible to intercept and copy quantum data used in because it is impossible rather to intercept and copy quantum data, and this concept is used in quantum key distribution in modern day quantum cryptography, and BB84 protocol is one of the important protocols which is used in quantum cryptography nowadays. Quantum teleportation, since the copy is not possible, since cloning is not possible, hence quantum teleportation is required to transfer quantum data. Quantum error correction, since the copying is not possible, cloning is not possible, we must use some other ways like entanglement or indirect methods instead of naive copying to achieve quantum error correction. So these are some of the implications of no cloning theorem. Let us come back to our basic topic of classical versus quantum communication. And again I say that in classical communication, the Shannon entropy quantifies the information in the form of a random variable. We want to know how much classical information we can extract from the quantum system. That is our goal basically. But the problem is that due to no cloning theorem and non-orthogonal states, right? Quantum measurements are probabilistic. So what happens basically? What is the situation? No cloning is not possible. Is the true result. States are non-orthogonal to each other. Because of that, if we try to measure the quantum state, what happens in that case? The quantum measurements lead to a probabilistic scenario. Therefore, the quantum measurements are probabilistic. We cannot with 100% certainty say that the measurement outcome is this particular measurement outcome, that the output state of the quantum system will be this eigenstate. So therefore we can say that the quantum measurements are probabilistic, and we cannot always perfectly recover the sent classical data in that case. So to take it further, let us try to define what is a quantum ensemble set. Alice sends classical information to Bob by encoding it into quantum states. So classical information is sent by encoding it into quantum states. The quantum ensemble is given by a set defined as the probability distribution. So what is that ensemble? What does this ensemble consist of? It consists of the probability distribution and the states. So what is this basically quantum ensemble? As I said that the quantum measurements are probabilistic, so the quantum state can be quantum state can be one of the possible states, possible states out of certain set of states, right? And every state can be the measurement outcome with certain probability. So Pi is the probability attached to the measurement outcome to a particular state, and rho I defines the state of the system. So one state, we attach a probability distribution to the measurement outcomes of different states, right? So where Pi is the classical probability with, of course, the total probability distribution summing to 1, and rho I is the quantum state. The quantum state can be pure or mixed. So the system is in state rho I with probability Pi, but we don't know exactly the value so what is the problem here? The problem here is that we don't know exactly the value of index I. That means we don't know exactly that which state after measurement the system will be in. That means we don't know this index I. We cannot say that the system after measurement is in state I. So therefore, the density matrix is a full mixture, a statistical mixture of messages. That means it is a statistical mixture of probability distribution corresponding to different states, right? So it is we can basically say that it is a statistical mixture of states with attached probabilities, right? Had it been a pure state, in that case the state is known and the density operator is just the outer product of that state. But since the quantum state is a statistical mixture of states, so therefore it leads to the quantum system to be in mixed state. So how do we represent the mixed state? Mixed state is represented by this. The density operator of the mixed state is summation of the product of the probability distribution and the outer product of the density operator, because every state in itself is a pure state. Of course it is attached with the probability distribution that leads to the mixed state. This is not quantum superposition. This is but a classical probability distribution over quantum states. So given an ensemble, so this is the ensemble given, we can find out the average ensemble, and this is given by the summation of the product of the probability distribution and the state of the system. Now with classical information, no hidden limits are attached, because we know that the amount of information that we can extract from the classical information is the Shannon entropy, and the Shannon entropy is basically denoted as Hx and is given by minus of sigma I pi log pi. This is a general entropy formula. This is the Shannon entropy. So that much classical information we can quantify with a certain message in classical world. But as far as the quantum information is concerned, limits are there due to the measurements. No matter what measurement techniques we apply, there are limitations attached to the measurement technique that we adopt. So there are two possible measurement techniques we can adopt. One is known as the projective measurement and the other is known as the positive operator valued measure, which is POVM measurement technique. So let us discuss these two techniques. The first is projective measurement. A projective measurement, also called as the von Neumann measurement, is defined by a set of orthogonal projectors. So we consider a set of orthogonal projectors, right? Set of orthogonal projectors represented by PIs, and each of these projectors satisfy the following characteristics: that they are idempotent, that the square of the projector is the projector itself, the adjoint of the projector is the projector itself, that means they are Hermitian also. They are orthogonal because Pi into Pj is equal to 0 for I not equal to j, that means the projectors are orthogonal, and they represent a complete system, that the summation of the probability distribution leads to identity. So these are the projectors that we will consider. So each projector Pi projects onto, so what is the role of this projector? Each Pi projects onto the eigenspace of the observable. Now what we are doing, we are trying to measure this property A. This is an observable, we are trying to measure it. How do we measure it? We project, we take this set of projectors and we project onto the eigenspace of A. What do we mean by that? What do we mean by the eigenspace of A? This observable A, basically it is a matrix, so definitely it will have certain eigenvalues that forms the eigenspace. So we will project these projectors onto the eigenspace of A associated with eigenvalues lambda I. So eigenspace is associated with these lambda i's, which are eigenvalues, such that the observable A is equal to the product of lambda I and Pi, the summation of all this product will lead to the observable. So this is how we will do the projection. We will use the orthogonal projectors onto the eigenspace of this observable A like this. But let us see how it works. So let the system be in ket psi, let the quantum system be in state ket psi, and we measure A. In that case, the outcome probabilities will be given by the magnitude squared of the inner product of pi versus pi with psi. So let us try to prove this. Let's take the right hand side. So right hand side is the norm square of the inner product of pi with psi, because the projector will be applied to the present quantum system, quantum state psi. So we can just segregate these two terms. By segregating these two terms and by applying the Hermitian property of the projector and the idempotent property of the projector, we can say that the probability comes out to be equal to this matrix element type of item, which is the inner product of this expression, right? So this is the result of the projective measurement. And what is the after we measure with the projective measurement, what is the state after measurement? So the present state ket psi will be leading to this state. So what is this? This is what does this state say? This expression says that the projector pi is applied on the present ket psi, right? So there will be a new ket vector which represents the state of the system, but of course the state of the system should be normalized with this vector. So when measuring a quantum state psi using projector pi, the post measurement state becomes, so this is the post measurement state. So we can prove this also. After measurement, the state collapses into the subspace corresponding to outcome I via the projector pi. The unnormalized state, so this is the unnormalized state, we will have to normalize it. So how do we normalize it? We will normalize it using the norm. So this is norm normalization being applied. So this is the norm and is given by the inner product of the expression inside, of course the under root, because the norm is equal to the square of the inner product. So if we do the manipulation, this will come out to the under root of the probability distribution, and of course this will be equal to, as we proved, pi is equal to this inner product of this expression. This expression, under root of this expression, the inner product of this expression will be used to normalize the measurement state after measurement, right? So previously it was ket psi, and after measurement the state will be defined like this. This process is known as the projective measurement. There is another process, and that is called as the positive operator valued measure, POVM. Now a POVM is a more generalized quantum measurement framework. It is defined by a set of positive semi-definite operators. So operators that we will use here are the semi-definite operators, a set of EIs acting on a Hilbert space. So these operators will act on the Hilbert space. Now what are the characteristics of these operators? These are positive operators, that EIs are greater than or equal to 0, and in turn it will lead to this matrix element being greater than or equal to 0. So this ket psi, which is the state, belongs to the Hilbert space, and of course the completeness. But the difference between the POVM and the projective measurement comes here. The EIs do not need to be orthogonal projectors, but in the previous case they were orthogonal and can be non-Hermitian also, or rank deficient. So the POVM technique is different from the projective measurement in terms of the projectors being non-orthogonal also and non-Hermitian also. So how it works? Let the system be in state rho being measured with POM. So the density operator is given, and we want to measure the system using the POVM technique. Now outcome probability will be given by, in this case, will be given by the trace of these two operators, which are, one is the projector and the density operator. Now if a quantum system is represented by rho I and the measurement is described by a POVM element EI, the probability of getting outcome I is given by this. So this is the probability. So there are two states, because the density operator can be in the pure state also, and it can be in the mixed state. So two cases we have to consider. First is the pure state. So in that case the probability, we say that the probability is equal to the probability of getting outcome I is equal to the trace of the multiplication of these two operators. So if we replace rho with the pure density operator, we will get this, and by using the cyclic property of trace, we will say that this comes out to be equal to the matrix the inner product of this expression, which we have already proved. So therefore this expression is correct, which is the probability of I. So therefore this is also correct, that the probability of outcome I is equal to the trace of the product of two operators, right, which is basically Born's rule of measurement, hence proved. And similarly we can do it, we can prove for the mixed state also, because mixed state is given by this. Earlier the pure state is given by the outer product of the ket psi with itself, and the once you now substitute for the mixed state, you can prove again to be correct. So therefore we can say that the probability of getting an outcome I after measurement is equal to the trace of EI and rho I, holds for all quantum states. Now there is a Holevo bound, that what is the maximum amount of information that we can measure, as was the case in the classical system, that Shannon entropy is the bound. But what is the bound in the quantum systems? Even if you know that the quantum state is prepared from a known ensemble, the receiver cannot always distinguish rho I perfectly, that we have already stated also, especially if the states are not orthogonal. Hence the central question arises that how much classical information we can extract from the quantum state by any measure. So again I am repeating the statement, that what is the statement of problem here that we are trying to solve. Now the accessible information is the maximum amount of classical information that can be extracted from an ensemble by performing a quantum measurement, let's say POVM. So this is the accessible information that we can extract using this measurement method from this ensemble, and this is given by, formally this is equal to maximum of course we are applying POVM, the mutual entropy I of x colon y is classical mutual information between x and y. What is x? X is the random variable of the prepared states, y is the classical outcome of the measurement. So we measure the accessible information in terms of the information theory concepts of mutual information and the random variables, where x is the random variable of the prepared state, y is the classical outcome random variable. So what is the mutual entropy between these two random variables? The accessible information will be equal to this. So best possible classical mutual information between preparation and measurement outcome. Now we define a term what we call as the Holevo bound, and this a key result is the Holevo bound. So therefore the accessible information will always be less than equal to this the chi epsilon basically, which is the Holevo quantity. So chi e is the Holevo quantity, and this Holevo quantity is described as the S rho. You can use here, I have used here rho, simple rho, but you can use the average rho also here. That will define the von Neumann entropy, average von Neumann entropy, but we can use, so S of rho is the von Neumann entropy basically, minus of this summation of this probability distribution Px, and the S rho x is the entropy in that particular state rho x, right. So we know that the von Neumann entropy is given by minus of trace of rho log rho. As I said, we can use the average rho factor also here, but that is subject to your convenience. So this is known as the von Neumann entropy, and if all these states are pure states, then of course the S of rho x will be equal to 0. If all these states are pure states, then this factor will be equal to 0, and our Holevo quantity will be equal to S of rho. So which is the Holevo bound? What is Holevo bound? So the Holevo quantity, or the accessible amount of classical information from the quantum system is bound by von Neumann entropy. So thus the amount of accessible information can never exceed the Holevo bound, no matter what measurement you are using. Either you are using projective measurement or POVM, this has to be at the most equal to the von Neumann entropy. Strictly speaking, it is often less than the Holevo bound. And this is Holevo bound, which is the von Neumann entropy, that says that tells us about the maximum information that we can extract from the quantum system as classical information. Thank you.